Bowfishing at night is a great option for a variety of reasons. For starters, you will encounter fish that seem less spooky, since they aren't sure what that bright object is bearing down on them. And oftentimes, you have the lake to yourself when all the other boaters go home. However, you will need to outfit your boat with lights and some special equipment to be truly successful when the sun goes down. But before I dive into the world of nighttime bowfishing, it's important to understand a few things about electricity. We'll start with amperage, voltage, and wattage. Amperage is the amount of electricity that flows through your circuit, which powers your load, and is commonly referred to in amps. If you need a lot of amps to power a device, you want to make sure that you also have the proper voltage and the right wire size to flow that electricity. Voltage is the amount of pressure that pushes electricity through your circuits. Imagine a water hose trying to fill up a bucket. If the pressure is low, it'll take a long time to fill the bucket, unless your hose has a big diameter. However, if you increase the pressure, or in this case the voltage, the bucket will fill up faster, and often you can get by with a smaller hose. Now, it's important to understand what voltage your devices should be run on, because too much or not enough voltage can also be a bad thing. Finally, wattage is the amount of energy that the load requires. Like your lights. A great example you often hear in bowfishing is, I'm running 100-watt lights. And that's where all three of these terms need to come together to ensure the proper setup. For example, you will also need to know the voltage that the light requires, and then calculate the corresponding amperage to ensure that all of the circuit's components are sized to carry the proper amount of electricity safely to the light. Now, I know that most people don't enjoy doing math, but the math involved in powering a load is not that complex. The term for the equation is the power formula under Ohm's law. And if you know two of the three measurements, it's always possible to figure out the third. And having all three will allow you to choose the right components to create the circuit. If you want to use the power formula to calculate the wattage, which is P in the formula, you need to multiply the voltage, V, by the amperage, I. And if you want to know the amperage, you will divide the wattage by the voltage. And finally, if you want to know the voltage, you divide the wattage by the amperage. So let's run through a couple of examples. Now, my buddy just gave me 4 LED lights to put on my boat. He said that the lights run at 12 volts and are 50 watts each. Great. We have 2 of the 3 components for our formula, which means we can figure out the amperage per light. Then we multiply that by 4, and we'll get our total amp draw. Now in this case, one light is going to draw 4.2 amps, and all 4 are going to draw 16.8 amps when all 4 lights are on. And since we're dealing with 12 volts, the easiest option is to hook them up to a battery. And my buddy told me to use the biggest deep cycle battery I can find at the store. So I found one that supports 120 amp hours. This means that if the battery is fully charged, it can discharge up to 120 amps in 1 hour before it discharges to an unusable voltage. Cool. That seems like a lot. I mean, we only need about 17 amps. But how do we actually know how long that's going to last? Well, your typical lead-acid deep cycle battery isn't meant to be discharged much more than 50% of its rating before being recharged, or it will significantly decrease the battery's life. So we really only have about 60 amp hours to safely work with. And if there were no other variables coming into play, you should be able to run your 4 lights for about 3.6 hours. Wait, I typically fish for about 5 hours, so I need more power. What if I just add another battery? It's a good idea. I mean, if you get a second battery and you hook it up in parallel with the first, you maintain 12 volts. And now you have 240 amp hours total and 120 usable amp hours, meaning you double your time on the water to 7.2 hours. But you also have the weight of 2 big batteries to contend with now. Hey, I remember that my buddy said that I can also run those lights at 24 volts. That's good. It gives us some options. But to get 24 volts, you still need 2 12-volt batteries. This time you connect them together in series. And you may be thinking, great, I just doubled my amp hours too. But unfortunately, no. I mean, you still have the same amount of amp hours to work with as what's listed on just one battery. Because in series, you get the same current, but at a higher pressure. meaning 120 amp hours at 24 volts. However, by recalculating the amp draw at 24 volts, each light goes down from 4.2 to 2.1 amps per light, or only 8.4 total amps. If we stay in the same safety window of 60 amp hours, we still get 7.2 hours of runtime. Now remember, this is for lead-acid batteries that are in good condition and fully charged. I'm planning to cover lithium iron phosphate batteries and larger battery arrays in another video. So what's better? Well, if you can't place your batteries close to your lights, you could get away with running a smaller gauge of wire with the 24 volt option, and this will save you money since heavy gauge copper wire can be expensive. Here's a chart that shows you the appropriate gauge of copper wire to use based on the distance the current needs to travel. And if you use wire that's too small, you can generate excessive heat that can melt the wire and possibly other components in the circuit as well. These are the basics for a direct current or DC lighting system. However, there are always other things to consider. For example, you may want the option to switch the lights on and off, and you may want to place a fuse in the circuit to protect your lights if something shorts. It's important to size these items too. Most of the cheaper 12 to 24 volt switches can pass up to 20 amps of current. And that's safe for the 4-light example above, but if you were to add more lights onto the same circuit, you will run the risk of melting that switch. And to avoid this, you should configure the lights into 2 or more circuits with separate switches for each. A fuse is also cheap insurance. Size the fuse to approximately 1.25 times the amp draw for the circuit, and it will fail before the other components get damaged. Place any fuses on your circuits in an accessible but protected spot close to the positive terminal of your battery. And in the event that a fuse blows, it's important to check the circuit over before simply replacing the fuse. You want to make sure that nothing looks like it's broken, or rubbed through, or corroded, especially on the negative side of the circuit. And if for some reason your fuse melts, you probably have too much amperage running in your circuit, and you should consider splitting the circuit up some more. Now, I know from experience that sizing your components appropriately and fusing them are the keys to avoiding on-the-water electrical challenges, and I've melted my fair share of fuses and switches and even wires in the pursuit of a stable circuit configuration. So I welcome any questions in the comments section below to help you avoid any of these pitfalls when getting started, or if you have a troublesome circuit that you're already dealing with. Now, in the next segment, we will cover AC lighting, as well as generator sizing and voltage converters, which allow you to run a DC system off of an electric generator for even longer fishing times. Don't forget to subscribe to the channel and drop a like if you found this information to be helpful. You can also follow us on Facebook at TWI Bowfishing, and we have a lot more great information on our website at twibowfishing.com. Check out more of our videos here, and thanks for watching.